That picking me up?
Yeah.
It's good?
Yeah.
All right. I have 30 minutes. Is that good? All right. Hello, everyone. I am Aaron Isaksen. I'm a PhD student at the NYU Game Innovation Lab. I'm the second author on this paper. First author is Rishabh Jain, who's a master's student. Christoffer Holmgård is a postdoc, and Julian Togelius is professor on the paper. So autoencoders are a type of neural network, and I didn't know if anybody here has neural network. If someone here is not an expert, I'm just going to go through a quick overview, not a lot of mathematics, but just the basics that we need for this talk. So the important thing to think about is neural networks as a magic box where you put in some input and you get out some output. And there's math in there, and there's nonlinear stuff, and there's fitness functions, there's machine learning, there's all sorts of goodies. We don't have to worry about that in this talk, okay? But what we do care about is that you give it some input data, and you also tell it what output you want. And then this magic box learns to create a mathematical function that anytime you give it some input, it'll try to create that same output. And the important piece to think about here is that the input and the output can be different number of dimensions. So we're going to put in an n-dimensional vector. Let's say it has 1,000 data points, and it's going to output something else. Maybe it has 3 data points or something. And the other thing that's nice about neural networks is that you can put them together. And so if you have an n-dimensional vector, and then it goes through one of these neural networks, and it comes out with a z-dimensional vector, and then you put it through another one, and it comes out with a k-dimensional vector. And when you're doing the training of the neural networks, you don't have to worry about how many different dimensions it's going through. But that's important when you're building these things because it lets you sort of do some nice tricks. Okay? And so just as an example, here's a picture of Mario, here's a picture of this turtle, and these guys, let's say, are 24 pixels by 48 pixels, and there's RGB, so that's 3. So this, you can think of Mario, this picture of Mario, as a 3,456 dimensional vector. Okay, and the turtle is also the same thing. And then you put it into the neural network, and oftentimes you'll see pictures like this, and each of these would be one of those dimensions. So this picture here shows 5, even though we're pretending it's 3,000. And then these arrows kind of represent that everything's all connected together in some complicated way. You go from a 3,000 dimensional vector down to a 1,000, and then out to a 2-dimensional vector. And what that 2-dimensional vector says is, what is the probability of it being Mario, and what's the probability of it being a turtle? So you put in this one, and you get out 100% Mario, and you put in this one, you get 100% turtle. And most of the time, neural networks use what's called supervised learning, which means that you give it a bunch of pictures of Mario, and you say these are all Mario. And you give it a bunch of pictures of a turtle, and you say these are the turtle. And the network learns to recognize Mario and learns to recognize the turtles. And what's cool about these things is they generalize, or one thing that's cool about them, is they generalize to new examples. So we feed in this picture of Mario, which it's never seen before, and it's carrying a hammer, but maybe that's a turtle shell. And the network might say, OK, now that's 95% Mario, and it's 5% turtle. Okay, so that's a pretty nice feature of these. Now, autoencoders are a particular type of neural network where the input dimension and the output dimension are the same. So you take in an n-dimensional vector, let's say the picture of Mario, and you output another picture of Mario. But what you do along the way is you try to make the input and the output match, which is just like an identity, right? Put in input, you get out the output. But along the way, you bring it down to a lower dimension. And so we're going to lose some information as it goes from the high dimensional down to a low dimensional, and then we're going to go from the low dimensional back up to the high dimensional space. And so one side of this is called an encoder, which goes from the n-dimensional down to the k, and then the other side is the decoder. And then the rest of this talk, we're going to be about all sorts of cool things you can do with these autoencoders. Okay, so we're going to talk about what you can do with this middle layer and why do you want to do this kind of thing. And before, when I was talking about neural networks usually being supervised, where you say, here a picture of Mario, and these are Marios, here a picture of turtles, and these are all turtles, we're going to use unsupervised learning here. So we don't actually say anything about the data we feed in. And clustering is sort of the common example of this, where you give it a bunch of data and you say to the clustering algorithm, hey, find out what is similar in the data. And so the algorithm says, oh, these things are near each other. Let's label them red. And these things are near each other. Let's label them green. So autoencoders work the same way. You just feed in data, and they find information they find correlations in your data. So now that we know about everything we need to know about neural networks, let's talk about the inspiration for this work and how we kind of got here. So neural style was a really big inspiration for this work that we started doing. In neural style, you take in a photograph of the, let's say, the Golden Gate Bridge, and then you feed it the style from different artists, and it's able to create an image using the content of one image and the style of another. And so this is one really nice technique of neural networks. And we were playing around with this, for video games, like what happens here, right? So you take the style of Zelda and the layout of a Mario level, and it creates this sort of like mashup thing where it's like kind of figuring some things out, right? Like the cloud is turned into a rock, which is kind of cool. So it seems like there's something going on, but this is all happening in the visual domain. We have no idea that what this little question block means, other than a collection of pixels. We really want to work more on a semantic level of level design. And here's another kind of a cool example, right, where you take the content of the castle and the style of Mario, and you can kind of get this sort of thing. But again, this castle doesn't really have any, it's not playable, right? So we need to be working at a different level. Another inspiration is deep dreams. In deep dreams, you have a neural network where it's trained to recognize things. So it's been trained to recognize cars and trucks and animals and buildings. And so then you pass an image to this thing, and you say to the neural network, OK, the area that recognizes trucks and buildings, I want you to modify the image so that you like it better, right? And effectively, like, you get more activated when you see this picture. And so it makes little changes to it that kind of it starts to dream up, so they say. So it dreams up cars and buildings that are in the image. And you keep running it through the same neural network over and over again, and it builds up these sort of pretty awesome pictures. So in games, what would that be, right? So Mario is a pretty nice demonstration where this neural network is evolved using neuroevolution, evolving topologies to learn how to play Mario. So it learns how to play the level. It randomly hooks together this neural network. And what we could do in a deep dreaming sense is say, OK, now that this neural network has learned to play Mario, what if we could take that and say, OK, this little section here, this is the part that avoids enemies. So now you let the neural network modify the level so that it enjoys it more, or that section of the neural network enjoys it more. And that would add more enemies to the level. Or there's another part of the neural network that's designed for, or that evolves for avoiding gaps. And so then if you tried to excite that level of the neural network, it would create a level with more gaps. Because this is the kind of direction we want to head. And the last thing to work on neural networks is the hype curve, right? So machine learning this year is right here in the peak of inflated expectations. It's about to be in the trough of disillusionment. So this seems like a good time to jump in and tie everything you can to neural networks. I'm sorry? No, this is a famous graph. It's called the Gettner, I think, or Gettner hype curve. Type in hype curve. They make one every year. It's pretty awesome. Big data used to be up here. Remember big data 2 years ago? It's not even on the graph anymore. All right, so OK, let's go back to autoencoders. So what we're going to do is we're going to feed in levels. We're going to encode them down to a low-dimensional space. We're going to decode them and try to get the same level back out. And what we're going to do is use Super Mario Brothers. And so here's the original level, and then we use something like the video game corpus, video game level corpus, or other. So, Mario AI competition has these levels in there too. And we just anything that's a block, we make a 1. Anything that's not a block, we make a 0. So we've lost the enemies. We've lost the knowledge that there's clouds here. That this is a different type of block than that. Doesn't matter. Let's just take 0s and 1s for now. Make it easy. As an aside, I'm the chair of the procedural content generation workshop. In our call for papers, we made a specific claim or request, please stop submitting Super Mario Brothers papers. But now that I've written one, I actually think that they're pretty important to do because it is nice to have a baseline, right? Like, no one really cares about making more Super Mario Brothers levels, but we do. It's really useful to compare other algorithms. So yeah, OK. That's my little political aside. So here's all the levels. We do the above ground levels, the below ground levels, the tree levels. We don't do any of the underwater ones because those are structured much differently. And what we don't want to do is feed in the entire level. Okay, there's just too much data here, and there's too much going on within the level. So what we're going to do is instead is make these little slices. So we're going to take these little level windows here, which are 14 tiles high, and they're 4 wide. And we can do all different sizes. You can try larger ones or smaller ones. In the beginning, we tried doing the whole screen, which is 16 tiles by 14. And the problem with doing a window that's about this big, a screen full, is that you end up getting like 2 different sort of semantic things happening on the screen at once. And that's kind of too much information for the autoencoder to learn. So it's better to kind of keep them about 4. And that was just us experimenting with different numbers to see what worked well. It's going to be different for different games. OK, so there's lots of things we can do with these autoencoders once we train them on the level windows. Oh, sorry, just to go back, just to clarify, we're going to put in a level window, which is a 4 by 14, and we're going to try to make that out, right? OK, and we'll just sweep along. We'll just take this, this, and this, and this, and train it on all the different windows for all the different levels. So one of the things you can do is, once you've built this neural network that learns how to take in a level window and output one, is that you can start to like add noise to this middle layer. So the level window gets transformed into something here, which is kind of strange. It's like a weird thing. But if you add noise to it, what you get out is new output. It's novel. It's like, it looks a lot like what the other data that it was trained on, but it has different characteristics. Something else that you can do is you can use this to recognize style. So you feed in the level window, and this lower dimensional thing here is kind of like a style identifier. It's sort of a fingerprint of what that level looks like. And there's a really neat trick called semantic hashing, where you can take the level window and you pass it down. You make this either a 0 or a 1, and this gives you like an n-bit vector, which sort of describes the level windows. And it does a really nice job of finding similarities. Something else we found this to be useful for is to do content repair. So this neural network really can only understand data that it's seen before. And so if you pass in new data that it hasn't seen, it tries to kind of like convert it into something that is reasonable or that it's already learned. So I'll go more into this about how this is useful. And then for mathy people, this is sort of like a nonlinear PCA, which is principal component analysis. So again, it can invert something that's high dimensional to something that's low dimensional, which is useful for visualization or just sort of understanding. There's also, these things are pretty good for doing lossy data compression. So you feed in the original level, it compresses it down to something smaller. You then store this. And then at the decompression stage, you take the decoder part, and it can reproduce the original data. And again, these days, we have lots of terabytes of data, so we don't really worry about it too much, although still games like No Man's Sky or something with 4 billion planets, you still do use compression, those kind of things. And it's kind of cool, because these learn like the perfect compression, in a sense, for the data that you're given it. This becomes trained just on the particular data you have, not on all data. It's not generic. And then finally, you can use this for some interesting design research. So I've done some work with analyzing like all possible variants of a game, specifically Flappy Bird we looked at. But we had to analyze Flappy Bird by hand and say, like, oh, here is a parameter, and here's a parameter. If you had 1,000 parameters in your game, this kind of system really wouldn't work. So what you could do is you can feed in all your parameters, and then use an autoencoder to bring it down to a much smaller set of knobs. You could then change just these 3, and you can see like what happens. So in Flappy Bird, the jump, velocity, and the gravity are really correlated. You can't change one of those without changing the other very much. And so those two, if this was gravity and this was jump velocity, they would be combined into one knob. And so again, the autoencoder will find this for us. We don't have to actually know what we're doing. OK, let's talk about some little details about training these things. I think I said this before, but there's 2 ways of doing this. One, you could take input windows, let's say they're 4 by 14, and then not have them overlap. But we found it to be better to make them overlap by 1. So you just create one level window, move it over by 1 tile, do it again. And then when you're reconstructing, you're going to have some overlap, right? So you can find different ways of saying if you have an overlap section, do you vote on it or whatever? There's lots of different things you can do. Another important parameter here is this: how big is this hidden layer? So do you have, how many variables do you have in there in the middle? And so this shows like what happens if you change that number. So in this case, we're doing windows of 1 by 14. Okay, so these are just single columns of Super Mario Brothers. And if you just had that middle layer only be a single node, then this is what it does. It compresses it down to one number and then uncompresses it. And you basically get a floor with some gaps. Okay, that's all you can do with just that one node. And as you start adding in nodes in that hidden layer, you start to, OK, now you can have obstacles that show up or things to hop over, and then we can start getting a lot more detail. And by 7, you're almost perfectly reconstructing it. There's a little screw up here in the final pyramid. But of course, by 14, it's like identity. You can do it perfectly. So somewhere around 8, it can do a perfect job. And that's because there's a lot of correlation in the data, right? It's not, Mario levels don't just have random noise. They actually have some structure. And so the autoencoder is learning that structure. Something else you have to worry about with neural networks is that if they learn the data too well, then it's called overfitting. And so all they can do is understand the data you train them on, and they have no ability to really do anything with new data. And so one way you can avoid this problem is by adding in noise during the training. So you feed it the uncorrupted data, and then you start screwing with it. And then while it's training, it's like, OK, I've got to compensate for this problem. And so it starts to make what's the word I'm looking for? I guess correlations and sorts of redundancies in the network in order to deal with this problem. And those redundancies are what help it later on deal with overfitting. And one thing that I didn't really know too much about neural networks, let's say a couple months ago before we started working on this stuff. And it's just a lot of engineering that you need. The math is certainly pretty helpful, but I think that just spending a lot of time with these and just trying different variables has really been a key to the success for this project. OK, so now let's go into some examples and some results. So let's do style recognition first. So in Mario, you have above ground levels, below ground levels, and tree levels. And the above ground levels, certainly one of the things that sets them apart is the ground, right? So this is something that you're going to see in a lot of these levels. Nothing on the ceiling, right? This open sky above. And we don't care about the graphics, so everything's going to get converted to 0 or 1. So it doesn't matter if this background's black or there's water here. That's just like, you can ignore that. So those are above ground levels. Below ground levels tend to have a roof on them and lots of stuff in the middle, like this, that kind of only shows up on the below ground levels. And then tree levels don't have a floor. So that's kind of like some unique style about these. OK, so what we're going to do for visualizing is we're going to build an autoencoder training on those levels. And we're just going to have 2 dimensions in the middle. And we're going to treat one as an x variable and one as a y variable. And so we can plot it on a 2D graph. OK, so now this next slide is a lot of information, but we're going to work through it. All right. So I've fed in a bunch of all the windows of all the levels. And I've told it not what level it comes from. Then I go through and I plot them in the autoencoder. I give them an x, and every window gets an x and y position. And then when I'm drawing them in this graph, I'm then going to label it with where it came from. So the triangles are above ground levels. Okay, it's above ground. See, this is an example window here, pointing to here. And there's a floor, and there's some stuff to jump on, but there's nothing on top. So that's an above ground level. The circles are below ground, so there's a roof. Okay, that's kind of part of what happens to the roof. And the square levels are the tree levels. There's nothing down there below. Okay, and the reason why some are filled and some are hollow is I wanted to do 2 examples. So I fed in 2, or in this image, I'm drawing hollow circles are from one of the underground levels, and filled are from another one. One of these from one tree level, the hollow are from another. And you can see that it's sort of learned some things, right? There's all over here is just underground stuff. And just here is only tree level stuff, and here is only above ground things. This section, it's all mixed up. So this is the stuff that's shared among different levels. And so if you go through the levels, you'll see that there are things like, there are parts of the underground levels that don't have a sky. And usually at the end of the tree levels, there's sort of a pyramid that you might have to run up. And so that's kind of why that stuff is shared. Okay, so again, here we haven't told it anything about which is trees. The autoencoder has just discovered that there's some similarities here. And so you could use this for style in the sense that if you were working on a above ground level and you wanted some suggestions, it might just pick out stuff from over here, right? Or generate more ideas by feeding in values from this area. And that would create things that were appropriate. If you're working on an underground level, it could generate things from over here and over here. And those would be new ideas, right? Like this space here doesn't appear at all in Super Mario Brothers, but it's probably something that would be relevant. All right, does that make sense? Cool. OK, level repair. So the idea here is you take an original piece of game and you add in something that's impossible to get through, and then you feed it through the neural network and it pops out something that is reasonable. Now, it didn't go through and remove this line and get back to the original, but it gave you something that is workable. And so I don't really think that there's be a lot of use in terms of like repairing things. I think level repair might not be the right word, but certainly making suggestions while you're making a level, and to have the system be able to say, like, here is some stuff that's similar and is relevant to what you're currently creating. Could be something useful. It doesn't work for everything. Like here, it can't figure out that you can't jump over this pit, right? It doesn't have that information in it. And I think the way to solve this is Adam Somerville is presenting something later this year at FTG Jigra, where what he did is he went through with an AI and he put in where the Mario needs to go into the maps. And so when you use, so then the autoencoder would learn where Mario needs to go, and then would only be able to generate levels where Mario can actually get through them. And so this is the technique I think that should be used for that. We haven't done this yet, but Adam has to good success. In terms of level generation, except before, autoencoders are pretty good at doing this sort of thing. So what we do here is we feed in all of the levels, all the level windows into the autoencoder, and we train it. And then we look at the distribution of data that happens in this middle layer. And these are just example distributions. They aren't actually what's coming out. But for this one, you might see that the data sort of is normally distributed around -4, and this one's normally distributed around 4, and standard deviations are different. And so we can capture all of that. And then what we can do is go into the encoder and generate new data that has the same statistical distribution as what we saw before, and they can create new stuff. And we can also go through and adjust the variance of these noise generators. And so here are some levels that are created using that technique. So this one has a very small variance, and it just kind of creates something pretty boring. And as you turn up the variance, you get more sort of unique stuff going on. Again, these, there's no guarantee that these are playable, but at least they are sort of reasonable. It shows that this technique is something I think, worth pursuing. So lots of future work to do here. First of all, clearly more than just blocks, right? We actually want to create the whole levels. This isn't too much of a challenge. You basically just need to have, at the end, have more channels. Or the beginning and in the end, you have more channels. So instead of just having 0 and 1, you have 0 and 1 for blocks, and then also 0 and 1s for if there's an enemy there, and also 0 and 1s if there's a coin there. And then you just make sure that only one of those can be set to 1 at a time. So that's kind of a solved problem. It's just an engineering effort to do. We definitely need better spatial awareness. Like when we create this, we don't really know. We don't care that these things are put next to each other. We just kind of like generate a bunch of stuff. And so this can be done with recurrent neural networks or long short-term memory neural networks. There's techniques for doing this to kind of have a better understanding that if something comes first, then you need to have something come later. And then really what we want to do is get a better understanding of that hidden layer. So really get into there and sort of understand what those knobs are, and to start to play with those and see if we can create new games or kind of go beyond 0 and 1. Like what happens when we go to 2 or -1, right? What's out in those spaces? OK, there's enough time for me to do some questions and discussion. So thank you. Clap for myself. I'm not sure why I did that. Yes.
I have 2 questions.
Yeah.
You talk about style identification and design parameter, like the Angry Bird example, like finding the design parameters, grouping them together. Why use unsupervised learning for that? Why not use supervised learning? Because you know what is a tree level. You have that information already. So why don't you tell it that it should cluster based on factors?
Because I know you don't really care so much about that it's a tree level. What I really care more about is I want to know, like, this section here is very different than this section here. Right? There's like a structure that's happening in this part that's not happening here. And so I want to, and same thing here too, right? Like this is like you have to slide it in here. And so it doesn't really generalize that well if you're going to say like tree. I agree with you that seems like a lot of work to do to just say this is a tree level. Because you could just say, like, check this pixel, and if this is a 1, then it's a, right? But the network has learned this, and that's sort of the thing that's, I think, is key, is that you just fed in data, and you let it kind of come up with the answers.
Well, do you think you could use your network as a novelty evaluator for levels?
I think it would work pretty well. I think that repair is sort of similar to that. In the sense we're not using it for that purpose, but I think that if the more that it changes the level in order to repair it, like the more novel it is. I think also in, where is it? Sorry. In this space here, you know, the distance you are from another space is certainly related to novelty. Again, you wouldn't do this in 2 dimensions. I think you would do this in 8 or 10 dimensions or something, but you know, you can do the math to sort of find things that way. And certainly unexplored sections. When I run this on like 16 dimensions, it doesn't just completely fill the space. Like there are parts that are hollow, and so, or empty, and so that would be the kind of novel areas to look into.
Question on the dimensionality reduction to get sort of these control knobs.
Yeah.
This might be covered by the neural network people, but in you mentioned this is sort of like a nonlinear PCA, and in I don't know, I guess what neural network people call classical techniques, people tend not to like PCA for that kind of thing because when you're purely minimizing reconstruction error, you don't have any guarantee that you're going to get interesting control knobs. They're often really highly correlated, so people use other stuff like independent congruence analysis instead, which gets statistically independent knobs. Have you looked at all, like, do you get interesting knobs here? Is it a problem? Do you know if there's solutions to that?
I mean, you do get interesting knobs in the sense that here are 2 knobs, and it does work, right? But we haven't done enough to like actually try to use these knobs as tools, right?
We don't know what these knobs are.
We don't know what they are. And I don't think in 2 dimensions they're not, you know, like there is some knob, like some one of these things here adds a roof, but only if it's set to be low, right? So yeah, that's definitely open work that we need to look into.
I should actually start setting up exactly that question, because that's where you need supervised learning in order for speed and what was it, like gap. You should have a supervised learning where you say it's more difficult now, or it's faster, or it's faster to finish, or you die more often. Something.
That could be one solution. The other thing I think is to really understand the math better. Like right now, when I'm doing this, I'm kind of using networks as a tool. But you can, when you're training them, you can make your loss function do things to reward it for making them independent. And I think that's probably what's happening.
Yeah, you could have things other than
right.
pure reconstruction.
Yeah, exactly. So I'm just doing like, you know, L2 reconstruction error, and it needs to do something more that rewards you for making sure that those are as independent or as orthogonal as possible.
You can keep talking, it's fine. Any questions?
Is there, no? Oh.
I was the only one with a question, sorry.
All right, thank you.